Dear ladies and gentlemen, my presentation is devoted to the contemporary state of the contact mechanics in terms of its practical use, and in particular to the method of dimensionality reduction. The standard formulation of contact mechanics is based on the so-called fundamental solution. This is a solution for the displacement of the surface of an elastic body under the action of a concentrated force. This displacement is given by this famous equation, where r is the polar radius, distance to the action point of the concentrated force, and E is effective elastic modulus. If there is arbitrary stress distribution on the surface, we can make use of superposition principle and sum up the displacement from many concentrated forces in form of an integral. And this is the first proceeding point for the solution of all contact mechanical problems. Of course, any stress distribution can be represented as a sum of concentrated forces, but this is not the only and not always the most convenient presentation. Another possibility is using periodic harmonic functions, and this is the basis of the Fourier transformation. It is basis of the fast Fourier transform based boundary element method, which is the golden standard of the contemporary numerical contact mechanics. Two approaches are absolutely equivalent because these are two parameterizations of stress. And there are infinitely large number of other parameterizations with other complete sets of basic functions. I will concentrate only one for the possibility which leads to the method of dimensionality reduction. It was invented by Jaeger. If we consider axisymmetric indenters, then indentation of such indenter can be represented as incremental indentations by flat-ended cylinders of increasing radius. And the basic functions are, in this case, the solutions for flat-ended cylinders. And these solutions are known for many kinds of media. If we use these basic functions, then we come to a very interesting method, very simple and fascinating method, which is called method of dimensionality reduction. This method was developed 2005 to 2013 and was crowned with a book on MDR, first in German edition, followed by the English edition and Chinese edition. And it was developed in detail in the last 10 years, 2013 to 2023. I will speak about the current state. I will give no derivations, but just start with description of how the method functions, works. We consider an axisymmetrical indenter in contact with elastic half space. It is not necessary that it is axially symmetric, but it is easier to start with axisymmetric profiles. And the procedure consists of replacing the true three-dimensional contact problem by a fictive one, which, however, will have the same contact mechanical properties. The first step is replacement of the three-dimensional indenter, the shape, by a plane shape, another plane shape, and this is made with the Abel transformation. This transformation is made only once for all further use. It can be normal, contact, tangential, contact, with viscoelastic adhesive and non-adhesive, or some dynamic process superposition of all this. And only once at the beginning there is transformation to the fictive. And then the second step is replacement of the elastic counterbody of the elastic continuum by a series of springs, of independent springs, elastic foundation. And the springs have the stiffnesses which are given here with red equations in normal and tangential direction. And the stiffness is defined by the separation between the springs, arbitrary separation, only enough, small enough, and the elastic moduli. Here in these equations, it is assumed more general situation than I started with, when both bodies are elastic, with elastic constants E1, E2, G1, G2, nu 1, and nu 2. And in the third step, this plane profile is indented in the defined elastic foundation. In this case, because of independency of springs, the solution is trivial. The displacement of individual springs is just the indentation depth minus the profile. The boundary of the contact is given by the condition that the displacement of the boundary springs is 0. From here, we become the relation between the indentation depth and the contact size, A, the contact radius. And this is one part of the solution of the contact problem. For arbitrary axisymmetric profile, because G we get from the shape, and then this equation is already some part in closed, complete form for arbitrary shape. And then we sum all the spring forces to give the normal contact force. In the table, you can see solutions for flat-ended punch, for parabolic body, this Hertz, classical Hertz problem, for conical profile, for power law profile, and for a parabolic profile with a small flat. The theorems of MDR tells us that the result obtained with this apparently toy model will always exactly coincide with the initial true three-dimensional solution. Now we considered axisymmetric profiles. Basically, the effective MDR profile can be defined for arbitrary shape. On the left, you see 4 axisymmetric profiles. The cross sections are shown with blue lines, and the effective, this transformed MDR profiles are shown with green lines. And on the right, you have a toroidal surface and the rough, some fractal rough surface, and the corresponding MDR profiles. How to determine the MDR profiles for complicated shapes is explained in this paper by Popov and Hess from 1960. But we remain a little bit with axisymmetric profiles. And what we did till now is the relation between normal force indentation and the size of the contact, but MDR allows also determination of the pressure inside the contact and the displacement of the surface outside the contact. All this is related to the normal contact. But there are many beautiful theorems which were discovered during the 20th century, which state that many other problems can be reduced, can be related to the normal contact problem. For example, to this category belongs the tangential problem. Its reduction to the normal contact problem was discovered independently by Cataneo in 1938 and Mindlin 1949, and for parabolic bodies. and in a very general form, 1995 by Jaeger. The adhesive problem can also be reduced to the non-adhesive normal contact problem. This was done 1971 by Johnson, Kendall, and Roberts, and later by several other authors for general axisymmetric profiles. And finally, 1955 and 1957, Lee and Radok have shown that the contact with viscoelastic media can be reduced to the contact of elastic bodies. And all these theorems are summarized in the MDR for generalized procedure with which we can handle all kinds of the mentioned problems. Yeah, this simplicity of the contact mechanics which appeared due to MDR allowed us to write this book, handbook of contact mechanics, where we gathered all known solutions for axisymmetric contacts obtained in 140 years since Hertz. What means all? All means all. All sensible solutions, normal, tangential contact, viscoelastic contacts, adhesive contacts with graded materials, functionally graded materials with various shapes. A selection of shapes is shown here, and there are not only the results, but the complete derivations. In the history, some of these derivations are very, very thick papers, but here there are a couple of lines because MDR simplifies, compactifies this procedure. Yeah, the MDR is so simple that one can explain it and teach to students of the first or second semester or use in the students' projects. And I really read such lectures since last 10 years. I just explained how it works, and now I would like to derive the equations of the MDR to show, to illustrate how it really works, how it functions. Yes. The fundamental element in the MDR is not a single force, but a flat-ended punch. And for such flat-ended punch, everything is known. The relation between force and indentation, the contact stiffness, which is proportional to the radius, A, the pressure distribution under the punch, the displacement outside the punch, and all this is known since 1885, derived by Businesque, 3 years after the well-known paper of Hertz. As a matter of fact, since the very beginning of the contact mechanics. And now if we consider some other shape and incrementally indent it into the medium, then it can, the first observation is that then we have always only one controlling parameter. For example, normal force, or indentation depth, or contact radius, and two other functions of the control parameter. For example, the indentation depth is a function of the contact radius. This relation does not depend on the elastic modulus. This is the most universal relation of all of them. And now we consider indentation, and it is sum of micro indentations, and the force at the end of the indentation process is the sum of incremental forces, integral of the n, but the force is a function of indentation depth, and indentation depth is a function of the contact radius. And so we can just go over to the integration over contact radius. Then we remember the derivative of the normal force by the indentation depth standing there in the integral is nothing but the contact stiffness of a flat-ended punch, which is known. And finally, we remember that d is g, d is equal to g of a, and we come to this equation. Integrating in parts gives the standard equation of the method of dimensionality reduction. This is the derivation, and in the same procedure, every other function, every other variable can be determined. For example, if, and due to this procedure, we have found what is the physical sense of the equivalent profile, G of A. This is just dependence of the indentation depth on the contact radius. Now, for example, let us take the pressure. The pressure under the punch is known since Boussinesq, and it is a function of the contact radius. And now we make indentations, and at each indentation, there's an indentation with a small indentation with a flat-ended cylinder with growing radius. So we sum up these pressures of flat-ended punches in form of integral, go from the integration of the indentation depth to the indentation of the contact radius. Remember that d is g, and so we have this final equation. And this is the equation for the pressure distribution, which I already have shown without derivation. And this is a derivation. And this procedure is applicable to any other properties. For example, if the pressure distribution inside the medium is known for the flat-ended punch, then we can get pressure distribution or stress distribution for any other shape by summing incremental functions over d, going from d to a, remembering that d is g of a, and this is the simulation of this incremental procedure. Maybe it is, maybe not. No, it was. Yeah, okay, it was shown how it is ending and how the stress is growing. It does not work. I think that all videos do not work here, but then the presentation is without videos. Now I would like to tell a couple of words about adhesive contact. Adhesive contact problem for parabolic bodies was solved in 1971 by Johnson, Kendall, and Roberts. And their solution based on the understanding that the boundary of the adhesive contact is equivalent to the Griffiths crack boundary. 1921, Griffiths created crack theory, the basis of the fracture mechanics. And the idea of Griffiths was that the crack boundary is in equilibrium if the energy, elastic energy, relaxed by small development, small replacement, small opening of the crack, is equal to the work of adhesion needed for this opening. This is energy balance idea. And the same idea was used by Johnson, Kendall, and Roberts. And the same idea is very simple to implement in the framework of the MDR. If the boundary is replaced by delta x, the distance between two adjacent springs, then two springs are released from the left-hand side and right side, and then the energy released by two springs energy stored in one spring is, of course, very easy to calculate. We relate to the work of adhesion of a ring-shaped area appeared due to opening, and get the criterion for the detachment of the boundary springs. There is no difference in the MDR between adhesive and non-adhesive contacts, with one only difference. There is no difference with one difference. Only the boundary springs, the displacement of the boundary springs is not zero, but has this critical value. So the displacement of the boundary spring is the critical value, and this is the equation which relates the size of the adhesive contact and the indentation depth. If we do this for the parabolic shape, we get, of course, the equations of Johnson, Kendall, and Roberts from 1971. We can also sum up all the springs to the new radius, and then we have normal force exactly equivalent to the GKR. It does even work. Now we can make this procedure with changing d, and we get the relation between normal force and separation distance, and it is exactly what Johnson, Kendall, and Roberts have made 1971. So now I come to the most recent development. I stated that one can use MDR also for non-axisymmetric contacts. If we are interested in the force displacement relations, then yes, the MDR profile and the MDR procedure can be used for absolutely arbitrary profiles. But stress distribution and displacement, only for axisymmetric. And we searched over 10 years for the solution, how to expand the MDR to non-axisymmetric profiles, and we have found this solution last year, 2021. And I will describe without derivation how it works. Yeah, derivation is a little bit abstract and complicated. It is based on Bette's reciprocal theorem of the Barber's extremal principle and Fabrikant's approximation for stress distribution under the flat-ended punch-off arbitrary profile. And I skip all these complications, just go to the description. So we now consider non-axisymmetric punch with the shape f of r and phi. If it would be axisymmetric, then it would be function only on the radius, and now it is a function of the azimuthal angle. Now, in the first step, we define effective equivalent axisymmetric profile just by averaging over the angle. This is not what I suggest, but this is the result of the derivation. Yeah, we should define this equivalent axisymmetric profile. Then we can consider the deviation of the true profile from the axisymmetric. Then we take the axisymmetric profile. For axisymmetric profile, we know how to apply the MDR. MDR is for axisymmetric profiles. So we define the equivalent profile. We get the size of the contact. We get the normal force. We get the pressure distribution. If we only interested in the force displacement relation, then this is the end of calculation, because the result of the theory is that the normal force for non-axisymmetric profile is the same as for equivalent axisymmetric profile. One can just replace it by axisymmetric, and this is correct normal force. And if we also need the shape of the contact and the pressure distribution, then we go to the step number 4. And here, now the shape is not a circle, not a constant, but some deviation, delta r. This radius depends on the phi. And this deviation is given by explicit equation shown there, derived with in this paper. And finally, the pressure of the axisymmetric solution is just scaled to the correct shape of the size of the contact shape. And here are comparisons of this theory of the MDR with a high-resolution boundary element. For this is the shape and the normal force as a function of indentation, the contact areas and the pressure distributions. So now I'm always in the end of my presentation, I told about the method of reduction. Yeah, what exactly reduces the method of dimensionality? Yeah, first of all, it replaces the three-dimensional system by a one-dimensional one. So a continuum field, three-dimensional continuum field with degrees of freedom by one-dimensional continuum field with degree of freedom. But even more important, these degrees of freedom are independent. And this means that practically it is reduced to one single degree of freedom. Not only one-dimensional system, but one single degree, independent springs. And this makes this method to a very convenient method of thinking about complicated contact mechanical problems. So it is, gives us a sort of intuitive knowledge of contact mechanics. Well-known philosopher Spinoza said that intuitive knowledge, the knowledge as if we see the things as they are in front of our eyes, gives also the highest possible mental harmony. So we can not only make use, it is not only useful, but it is a real joy of life. So let us achieve the highest harmony by seeing, by using this simple tool, by seeing what lies in front of our eyes. Yeah, thank you.
Okay.